So in this lesson, we're going to talk about a new data structure called priority queues. So we start with a simple question. What if there's a data structure that can always find min of a set efficiently? So that's an interesting question, because if you have an array which is not sorted, finding a min would require big O of n operations. So we don't consider that to be efficient. Now, if you have an array that is sorted, you can find the min in big O of 1. We consider that to be efficient. But keeping something sorted is a very big requirement, and very expensive. So we know even the best sorting algorithm requires n log n. So what do we think about a data structure that can always find the min of a set efficiently? Maybe perhaps in big O of log n or big O of 1. So let's think about that question. Now, before we get there, let's talk about the complexity of operations with the data structures we know. Now, it never hurts to revisit this table again and again, because it gets you to think about some of the most common operations you do, such as insertions, searching or finding, removing something, finding max and min. So in terms of an array, which is an arbitrary array, we know that inserting something to an array can be done in big O of 1. How do we do that? We just stick the element to the back of the array. Finding something in an unsorted array would require big O of n. It requires us to look through the entire array to find this. Removing something would require for you to look for it. That itself would cost you big O of n. But then you'll have to adjust the array to make sure that the hole is filled. And max and min, finding max and min in an unsorted array would require big O of n. Now, if you have a sorted array, you can do insertions, still would require big O of n now, since we have to maintain the invariant of sorted. And finding something in a sorted array using binary search can be done in log n time. Removing something in a sorted array would require big O of n, since we'll have to find it and we'll have to adjust the array to remove it and maintain the sorted invariant. Max and min, we know, is at the end of the array, so therefore you can find max and min in big O of 1. When it comes to linked list, you can insert something to a linked list, the front of the list in big O of 1. Finding would require you to traverse the list. Remove require you to traverse the list and remove it. And finding max or min will require you to look at all the elements in the list. So the complexity of operations go as O1, On, and so on. If you have a sorted linked list, it doesn't give you any advantage. In fact, you will have to maintain the sorted invariant after you insert. So that would require big O of n. You will have to navigate through the list and find the place and maintain the sorted invariant. Finding would require big O of n. Removing would require big O of n, since you'll have to look. And max or min would require find big O of n. Now, when it comes to stack, what we mean by insert means we push something into the stack. That is big O of 1. Finding means that you will have to look, if you're looking for any element in the stack, you will have to pop all the elements from the stack and then look for this element that would cost you big O of n and put the stack back into its original shape. Removing something from the stack only can be done from the top, which we call pop. So that's big O of 1. Max or min from a stack would again require you to look through the entire stack by popping elements and pushing them back into the original format. So that's big O of n. When it comes to queue, inserting means n-queuing elements, which is big O of 1. Finding something would require, similar to stacks, a big O of n operations. You'll have to dequeue, look at them, find this element, and you will have to put the queue back to the original shape. Removing is dequeuing the element, so that can be done in big O of 1. Finding max or min would be similar to finding any other element. We'll have to traverse through the